Imagine standing beneath a star so massive that if you placed it where our Sun sits right now, its surface would stretch past the orbit of Saturn. Think about that for a moment. Not just past Mars, not just past Jupiter, past Saturn. Today we're going on a journey to meet the largest star ever discovered in our universe. If you're the kind of person who looks up at the night sky and wonders what's really out there, you're in the right place. Hit that subscribe button and give this video a like. Now let's get started. The universe doesn't hand us easy answers. When you're trying to measure something that's thousands of light years away, something so bright it would vaporize any spacecraft we could send toward it, something that literally defies the laws of physics as we understand them, you run into problems. And that's exactly what astronomers have been grappling with. Let me paint you a picture of what we're dealing with here. Our Sun, the star that gives us life, that lights up our days and makes everything on Earth possible, has a radius of about 696,000 kilometers. That's already pretty impressive, right? You could line up 109 Earths across the face of the Sun. 109. And we think of Earth as a pretty decent-sized planet. But compared to the stellar behemoths we're about to discuss, our Sun is like a grain of sand on a beach. Actually, that comparison doesn't do it justice. It's more like comparing a marble to a hot air balloon. And even that falls short of conveying the true scale of what we're talking about. The stars we're exploring today belong to a special category called red supergiants. These are stars that have lived fast and are approaching the end of their lives in the most dramatic way possible. They've burned through the hydrogen in their cores, started fusing heavier elements, and in the process they've swollen to absolutely staggering proportions. Their outer layers have expanded so far from their cores that the surface temperature actually drops, giving them that characteristic red color. Think of it like this. Imagine you're blowing up a balloon. As you add more air, the rubber stretches thinner and thinner, spreading out over a larger area. The material is the same, but it's distributed differently. That's somewhat similar to what happens with these red supergiants, except instead of rubber and air, we're talking about stellar material and nuclear fusion powered by forces that would make our most powerful bombs look like firecrackers. But here's where our story takes an unexpected turn. In science, we don't just accept things because they sound cool or because everyone's saying it. We question, we measure, we test. And when new data comes in, we have to be willing to change our minds. That's not weakness, that's strength. That's how we get closer to understanding what's really happening out there in the darkness between stars. For a long time, a star called Scuti held the crown as the largest known star in the universe. Discovered back in 1863 by German astronomers at the Bonn Observatory, Scuti sits in the constellation Scutum, about 9,400 light-years from Earth. Early measurements suggested it had a radius roughly 1,700 times that of our Sun. 1,700 times. Wrap your head around that. If you replaced our Sun with Scuti, its surface would extend beyond the orbit of Jupiter. Earth, Venus, Mercury, Mars, Jupiter, all of them would be inside the star. We'd be swimming in stellar plasma if we could somehow survive, which we absolutely couldn't. The sheer scale makes you feel incredibly small, doesn't it? But also, somehow, part of something magnificent. Astronomers fell in love with Scuti. It became the poster child for big things in space videos, articles, and documentaries. And honestly, who could blame them? The star was visible, relatively well studied, and its size was genuinely awe-inspiring. For years, it sat comfortably on its throne as the largest star we knew about. But then came Stephenson 218. Discovered in 1990, Stephenson 218, also called Saint 218, or RSGC 218, resides in the Stephenson 2 cluster, located roughly 19,000 light-years away in the Scutum Centaurus arm of our Milky Way galaxy. Initial calculations based on its luminosity and distance suggested this star might be even larger than Scuti. Some estimates put its radius at around 2,150 times that of our Sun. 2,150 solar radii. Can you even picture that? If Stephenson 218 replaced our Sun, its surface would reach nearly to the orbit of Saturn. Saturn, that planet with the beautiful rings, the one that sits 1.4 billion kilometers from the Sun. That's how far this star's surface would extend. The internet went wild. Videos proclaimed Stephenson 218 as the undisputed heavyweight champion of the universe. Graphics showed it dwarfing everything else. It became the new standard for cosmic comparisons. UY Scuti was yesterday's news. We had a new king. But science, real science, doesn't care about hype. It cares about data. And when astronomers started looking more carefully at Stephenson 218, they began noticing some problems. Big problems. See, there's this thing in stellar physics called the Hayashi Limit. Without getting too deep into the mathematics, the Hayashi Limit essentially describes the maximum size a star can reach while still maintaining stability. It's based on the star's mass, luminosity, and temperature. Push past this limit, and the star becomes unstable. Its outer layers can't hold together. The physics just doesn't work anymore. When researchers crunched the numbers for Stephenson 218 using its supposed size, they hit a wall. The star was too big. According to the laws of stellar physics as we understand them, a star that massive and that large shouldn't exist. It would have torn itself apart long ago. Something wasn't adding up. Then came the Gaia Space Telescope. Launched by the European Space Agency in 2013, Gaia has been on a mission to create the most detailed, three-dimensional map of our galaxy ever made. It measures the positions, distances, and movements of stars with unprecedented precision. And when Gaia turned its instruments toward the Stephenson 2 cluster, it delivered some surprising news. The distance to Stephenson 2 was wrong. Not slightly wrong, significantly wrong. Earlier measurements had placed the cluster at about 19,000 light-years away. But Gaia's data suggested it might actually be closer, somewhere around 11,000 to 13,000 light-years from Earth. Now, you might be thinking, what's a few thousand light-years between friends? But in astronomy, distance is everything. Here's why that matters. When we calculate a star's size, we rely heavily on its distance from us. We measure how bright it appears from Earth, then use the distance to figure out how bright it actually is at its surface. From that intrinsic brightness, combined with temperature measurements, we can estimate the star's size. If the distance is wrong, everything else falls apart like a house of cards. With the corrected distance from Gaia, astronomers had to recalculate Stephenson 218's size, and when they did, the numbers came tumbling down. Instead of 2,150 solar radii, the star might actually be somewhere around 1,050 to 1,200 solar radii. Still enormous, don't get me wrong. Still one of the largest stars we know of. But not the champion. Not the absolute biggest. This is where science gets beautiful, though. Some people might see this as a failure, as scientists being wrong. But that's not what's happening here. This is science working exactly as it should. We gather data, we make the best estimates we can with what we have, and then when better information comes along, we update our understanding. There's no ego in good science. There's only the search for truth. So if Stephenson 218 isn't the largest star, and if UY Scuti's measurements also have some uncertainty, then what is? What star can we point to and say with confidence, that one? That's the biggest? Enter RSGC1 F01. Now, I know what you're thinking. That name doesn't exactly roll off the tongue. It's not as catchy as UY Scuti or as dramatic sounding as Stephenson 218. But sometimes the most important discoveries come with boring names. RSGC stands for Red Supergiant Cluster, and this particular star, designated F01, sits in the first such cluster ever discovered. RSGC1 was identified in 2006, and let me tell you, finding it was no easy task. This cluster sits about 6,000 parsecs from Earth. That's roughly 19,500 light-years, located in the Scutum constellation. The cluster itself is hidden behind enormous clouds of dust and gas, making it nearly impossible to see with optical telescopes. The dust absorbs visible light, blocking our view like fog on a highway. But here's where human ingenuity comes in. We can't see through the dust with visible light, but infrared light passes through much more easily. Infrared telescopes can peer through those cosmic clouds and reveal what's hiding on the other side. And when astronomers used infrared surveys to look at this region, they struck gold. They found a cluster containing at least 14 red supergiant stars, one of the highest concentrations of these stellar giants ever discovered. Among these titans, one stood out: RSGC1 F01. Based on careful measurements of its luminosity, temperature, and spectral characteristics, astronomers estimate that F01 has a radius of approximately 1,460 to 1,540 solar radii. Some studies suggest it could be even larger, potentially reaching 1,910 solar radii under certain models. But let's stick with the conservative estimates because in science, it's better to be cautious than sensational. 1,500 solar radii. If you placed F01 where our Sun sits, its surface would extend past the orbit of Jupiter, reaching somewhere between Jupiter and Saturn. Everything interior to that, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, would be engulfed in stellar material. But here's what makes RSGC1 F01 special, beyond just its size. The measurements we have for this star are more reliable than those for many other candidates. Why? Because we have better data on the cluster's distance, better understanding of the dust extinction affecting our observations, and multiple independent measurements that agree with each other. In science, consistency matters. When different methods and different teams arrive at similar conclusions, that's when we start to feel confident. Think about what this star represents. RSGC1 F01 is so large that light takes over 7 hours to travel from one side of the star to the other. 7 hours. Light, moving at 299,792 kilometers per second, needs 7 hours to cross this star's diameter. In that same time, light travels from the Sun to beyond the orbit of Pluto and back. The volume of this star is almost incomprehensible. You could fit roughly 6 billion of our suns inside RSGC1 F01. 6 billion. If our sun were a basketball, F01 would be a sphere about 1.5 kilometers across. That's not a typo. 1.5 kilometers. You could put a small town inside that sphere. But despite its enormous volume, F01 probably doesn't have an equally enormous mass. That might seem contradictory, but remember what I said earlier about red supergiants being like stretched balloons. These stars have expanded so much that their outer layers are incredibly thin, barely denser than a laboratory vacuum here on Earth. Most estimates suggest F01 has a mass somewhere between 12 to 25 times that of the Sun. Massive, yes, but not proportional to its volume. This low density has profound implications. The surface gravity on RSGC1 F01 is incredibly weak. If you could somehow stand on a solid platform at the star's surface, and you absolutely couldn't for about 1 million different reasons, you'd weigh almost nothing. The star's immense size combined with its relatively low mass means gravity at the surface is just a tiny fraction of what we experience on Earth. This weak gravity also means the star is constantly losing mass. Stellar winds blow material away from F01 at thousands of kilometers per hour, carrying away the equivalent of Earth's mass every few thousand years. The star is literally evaporating into space, surrounding itself with shells and clouds of gas that will eventually enrich the interstellar medium with heavy elements forged in the star's core. And that brings us to something truly profound. Every atom in your body that's heavier than hydrogen or helium, the carbon in your DNA, the iron in your blood, the calcium in your bones, was created inside a star. Not just any star, but massive stars that lived, died, and exploded billions of years ago. Stars like RSGC1 F01 are cosmic factories, taking simple elements and fusing them into the building blocks of planets, oceans, and people. When you look up at the stars tonight, you're not just seeing distant points of light. You're seeing your ancestors. You're seeing the furnaces that created you. We are, quite literally, made of stardust. And stars like F01 are continuing that ancient tradition, even now, preparing to return their enriched material to the galaxy when they eventually explode. Because that's the fate awaiting RSGC1 F01. This star is in the final stages of its life. Red supergiants like this one don't fade away quietly. They're destined to become supernovae, cataclysmic explosions so bright they can outshine entire galaxies for a brief moment. When F01 explodes, and it could happen tomorrow or 100,000 years from now, we can't know for sure, it will release more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. That explosion will be visible across the galaxy. It might even be visible from Earth in broad daylight, depending on exactly when it happens and how we're positioned. The blast wave will tear through space at a significant fraction of the speed of light, slamming into surrounding gas and triggering the formation of new stars. From death comes birth. From endings come beginnings. But we're getting ahead of ourselves. Let's stay with F01 while it's still alive, while it's still holding itself together against the inexorable pull of gravity and the outward pressure of fusion. Living on a planet orbiting a star like RSGC1 F01 would be a very different experience from life here on Earth, assuming life could even exist there, which is extremely unlikely. The star's enormous size means it has a huge surface area radiating heat. Despite its relatively cool surface temperature of around 3,500 Kelvin, cool for a star anyway, still hot enough to vaporize any known material, the total energy output is staggering. And that uncertainty, that limitation in our measurements, is actually something beautiful. It reminds us that the universe still has secrets. There are still mysteries waiting to be solved, questions we haven't fully answered, in an age where it sometimes feels like everything has been discovered, where you can look up any fact instantly on your phone. It's humbling to know that the cosmos still surprises us. Think about what we've accomplished, though. We're standing on a planet orbiting an average star in the outer reaches of a galaxy containing hundreds of billions of stars. And from here, using nothing but light that's traveled thousands of years to reach us, we've figured out that certain stars are more than 1,000 times larger than our own. We've measured their temperatures, their compositions, their masses. We've traced their life cycles from birth to death. That's extraordinary. It's worth pausing to appreciate the tools that make this possible. The telescopes, both ground-based and space-based, that gather starlight and break it into spectra. The satellites like Gaia that map stellar positions with mind-boggling precision. The computer models that simulate stellar evolution and help us understand what's happening inside these giants. And most importantly, the astronomers, human beings, people with families and hobbies and morning coffee routines who dedicate their careers to unraveling these cosmic puzzles. Science is a human endeavor. Behind every measurement, every calculation, every discovery, there are people. People who stayed up late running calculations. People who spent years writing proposals for telescope time. People who felt the crushing disappointment when an observation failed and the soaring elation when new data revealed something unexpected. The universe doesn't interpret itself. We do that. We're the ones asking questions and seeking answers. And sometimes those answers lead to more questions. For instance, why do some stars become red supergiants while others don't? Why do some supergiants get larger than others? What determines the maximum possible size for a star? That last question brings us back to the Hayashi Limit I mentioned earlier. Named after Japanese astrophysicist Chushiro Hayashi, this limit represents a fundamental boundary in stellar physics. As a star expands, its outer layers cool down. If the layers get too cool and too extended, they become unstable. Convection, the churning motion of hot material rising and cool material sinking, dominates the star's structure. Push too far, and the star can't hold itself together. The exact position of this limit depends on the star's mass and composition, but current models suggest stars can't exceed radii of about 2,000 to 2,500 solar radii while maintaining stability. RSGC1 F01, at 1,500 solar radii, sits comfortably below this limit. Stephenson 218, with its original estimated size of 2,150 solar radii, was pushing right up against it, which was one of the red flags that suggested the measurement might be wrong. But here's a fascinating wrinkle. The universe isn't always bound by what we think is possible. Throughout history, astronomers have discovered objects that challenge theoretical predictions. Pulsars, black holes, exoplanets, all of these either seemed impossible or weren't predicted before we found them. So while theory suggests stars can't exceed a certain size, we have to remain open to the possibility that nature might surprise us again. Could there be stars out there even larger than RSGC1 F01 that we simply haven't discovered yet? Absolutely. Our galaxy is enormous, containing an estimated 200 to 400 billion stars. We've studied in detail maybe a few million of them. That means we've examined less than 0.001% of the stars in our galaxy. The Milky Way is a big place, and there are plenty of regions we haven't surveyed thoroughly. Many of the largest stars are hidden in dusty regions like the one concealing RSGC1. These stellar nurseries and clusters are shrouded in gas and dust, invisible to optical telescopes. We've only begun systematically surveying the galaxy in infrared light over the past couple of decades. Who knows what we'll find as those surveys continue? And that's just our galaxy. There are an estimated 2 trillion galaxies in the observable universe. 2 trillion, each containing millions, billions, or even hundreds of billions of stars. The sheer scale is almost paralyzing if you think about it too hard. Somewhere out there, in a galaxy billions of light-years away, there might be a star that makes RSGC1 F01 look small. We'll never see it. We'll never measure it. But it might exist. That's the beauty and the frustration of astronomy. The universe is bigger than we can ever fully explore. There will always be more to discover, more to understand. Every answer generates new questions. Every discovery reveals new mysteries. But let's bring things back to what we can observe and measure. Beyond RSGC1 F01 and the other red supergiants we've discussed, there are other contenders for the title of largest star, each with their own measurement uncertainties and controversies. VY Canis Majoris, for example, was once thought to be the largest star. Located about 3,900 light-years away in the constellation Canis Major, VY Canis Majoris is a red hypergiant, an even more extreme category than red supergiant. Early estimates put its size at around 2,800 solar radii, but more recent studies suggest it's probably closer to 1,420 solar radii. Still enormous, but not quite the record holder it was once thought to be. What makes VY Canis Majoris particularly interesting is its complex surrounding nebula. The star has been ejecting mass in asymmetric, explosive bursts, creating intricate structures of gas and dust around it. High-resolution images from the Hubble Space Telescope reveal arcs, filaments, and knots of material stretching across light-years. It's a star in its death throes, unstable and violent, giving us a preview of what might await RSGC1 F01 in the future. Then there's WOHG64, a red supergiant in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. WOHG64 has the distinction of being the first star outside our galaxy to have its diameter directly measured. Using the Very Large Telescope Interferometer in Chile, astronomers combined light from multiple telescopes to achieve resolution fine enough to actually see the star as a disk rather than a point. The measurement? Roughly 1,540 solar radii, very similar to RSGC1 F01. What's remarkable about WOHG64 is that it's surrounded by an enormous, dusty torus, a donut-shaped cloud of material. This torus is so large that if you placed it in our solar system, it would extend from the Sun to beyond the orbit of Saturn. The star is apparently shedding material at a prodigious rate, and that material is forming this massive circumstellar structure. It's another piece of evidence showing us how these giant stars interact with their environments, how they shape the space around them. Each of these stars, RSGC1 F01, VY Canis Majoris, WOHG64, UY Scuti, tells us something important about stellar evolution. They represent different stages, different masses, different environments. By studying them as an ensemble rather than individually, we build a more complete picture of how massive stars live and die. And that's really what astronomy is about. It's not just collecting facts and figures. It's not just saying, this star is bigger than that star. It's about understanding the processes, the physics, the story of how the universe works. Every star is a laboratory where we can test our theories about matter, energy, gravity, and time. Consider what's happening right now inside RSGC1 F01. Deep in the core, temperatures exceed 100 million Kelvin. At those temperatures, atomic nuclei slam together with enough force to overcome their electromagnetic repulsion and fuse. Carbon nuclei combine to form neon and magnesium, releasing energy in the form of gamma rays. Those gamma rays ricochet through the dense stellar interior, gradually working their way outward. It takes thousands of years for energy created in the core to reach the surface. A photon, a particle of light, doesn't travel in a straight line through the star. It gets absorbed and re-emitted countless times, bouncing around like a pinball. The distance from core to surface might only be a few 100 million kilometers, but the actual path a photon takes could be trillions of kilometers long. By the time that energy finally reaches the surface and escapes into space, the photon has been transformed. What started as a high-energy gamma ray might emerge as visible light or infrared radiation. And some of those photons, after traveling through space for 19,500 years, enter a telescope on Earth. They pass through lenses and mirrors, hit a detector, get converted to electronic signals, and eventually form an image on a screen where a human astronomer sees them. That astronomer might measure the brightness, analyze the spectrum, compare it to models, and publish a paper. Other scientists read the paper, critique it, suggest improvements. The measurement gets refined, our understanding deepens, and all of this happens because a photon, born in the hellish core of a dying star almost 20,000 years ago, completed its journey and told us a tiny piece of the cosmic story. There's something profoundly moving about that connection. You, sitting wherever you are right now, are connected to RSGC1 F01 through light, through physics, through the simple fact that we live in the same universe, governed by the same laws. The atoms in your body and the atoms in that distant star were forged in similar furnaces, scattered by similar explosions, and eventually found their way to their current locations through the grand cosmic dance that's been going on for 13.8 billion years. Speaking of which, let's put RSGC1 F01 in historical context. When did this star form? How long has it been shining? Based on the age of the cluster it resides in, RSGC1 appears to be between 10 and 20 million years old. That means the star itself is probably somewhere in that age range as well. 10 to 20 million years. Humans have only existed for about 300,000 years. Recorded history goes back maybe 5,000 years. The dinosaurs went extinct 66 million years ago. So RSGC1 F01 is younger than the dinosaurs, but older than almost everything else we can point to in Earth's recent history. When this star was born, Earth was in the Miocene epoch. Early apes were beginning to evolve. Grasslands were spreading across continents. The climate was warmer than today, and the continents were still slowly drifting toward their current positions. On Earth, life was abundant and diverse, but nothing remotely human existed yet. And in a cluster 19,500 light-years away, a cloud of gas and dust began to collapse under its own gravity, perhaps triggered by the shockwave from a nearby supernova, or maybe just because the cloud reached a critical density. regions within it started to fall inward. As material compressed, it heated up. Temperatures rose, and eventually, in multiple locations throughout the cloud, conditions became extreme enough for fusion to ignite. Stars were born. One of those stars was RSGC1 F01. At birth, it was hot, bright, and blue, a massive O-type or B-type star, probably 15 to 25 times more massive than our Sun. It quickly blew away the surrounding gas with its intense stellar wind and ultraviolet radiation, revealing itself to the universe. For millions of years it burned steadily, fusing hydrogen into helium in its core. But that phase is over now. The star has exhausted its core hydrogen and transitioned to fusing heavier elements. It's swollen to its current enormous size, become cooler and redder, and entered the final chapter of its life. In cosmic terms, it's an old star approaching death. In human terms, it's still been shining since before our ancestors climbed down from the trees. And here's something mind-bending to consider. The light we see from RSGC1 F01 left the star 19,500 years ago. That means we're not seeing the star as it is now. We're seeing it as it was during the last ice age on Earth, when humans were still hunter-gatherers, when woolly mammoths roamed the northern continents, when the first cave paintings were being created in places like Lascaux and Chauvet. The star as it exists right now, in this very moment, we won't see that version for another 19,500 years. It's entirely possible, maybe even likely, that the star has already exploded. The supernova might have happened centuries ago or millennia ago, and the light from that explosion is still traveling toward us through the darkness of space. One day, maybe in our lifetime, maybe not for generations, that light will arrive. And suddenly, there will be a new bright star in the sky where none existed before. Ancient astronomers called these novae, new stars, not understanding that they weren't new at all, but rather old stars dying. When a supernova appears in our sky, it's a message from the past, a postcard from a star that met its fate long before the light reached us. It's the universe's way of reminding us that distance and time are intimately connected, that looking out into space is looking back in time. This time delay applies to everything we see in space. The Sun is 8 light minutes away, so we see it as it was 8 minutes ago. The nearest star system, Alpha Centauri, is about 4.3 light-years away, so we see it as it was 4.3 years ago. The Andromeda Galaxy is 2.5 million light-years away, so we see it as it was when our ancestors were just beginning to use stone tools, and the most distant galaxies we've observed are over 13 billion light-years away, showing us the universe as it was when it was less than 1 billion years old. We are, in a very real sense, time travelers. Every time we look up at the night sky, we're looking into the past, and the farther we look, the further back in time we see. Astronomy is a form of archaeology, except instead of digging into Earth to uncover the past, we're looking outward into space. Now, you might be wondering, with all this talk of enormous stars and cosmic distances and light travel time, what does any of this have to do with your daily life? Why should you care about a star 19,000 light-years away that you'll never visit, and that might not even exist anymore? That's a fair question. And the answer is both simple and profound. We care because we're curious, because we're human, because asking questions about the universe is part of what makes us who we are. For all of human history, people have looked up at the stars and wondered. Ancient cultures created myths to explain the lights in the sky. They built monuments aligned with celestial events. They used the stars for navigation, for timekeeping, for predicting the seasons. The stars weren't just pretty lights. They were fundamental to survival and to making sense of existence. Today we have a different relationship with the cosmos. We've moved beyond mythology into science. But the fundamental impulse is the same. We still look up and wonder. We still ask questions. What are those lights? How far away are they? What are they made of? How did they form? Where did we come from? Are we alone? These are deep questions, questions that touch on philosophy and meaning as much as they touch on physics and chemistry. And studying stars like RSGC1 F01 helps us answer them. When we learn about stellar evolution, we're learning about our own origins. The carbon, nitrogen, oxygen, iron, and dozens of other elements that make up your body were created inside stars. Every breath you take involves oxygen atoms that were once inside a star's core, forged through nuclear fusion, then scattered into space when that star died. You are quite literally made of stardust. That's not poetry. That's fact. Understanding how stars work, how they create elements, how they live and die and enrich the galaxy with their remains, this helps us understand where we came from. It places us in context. We're not separate from the universe, looking at it from the outside. We're part of it. We're the universe looking at itself, trying to understand itself. And that realization, that sense of connection and perspective can be transformative. It can make your problems seem smaller, yes, but it can also make your existence seem more meaningful. You're not just a random collection of atoms. You're a way for the cosmos to know itself. You're billions of years of cosmic evolution manifested in conscious form. You're a pattern that the universe has created, a pattern capable of looking back at the stars and understanding what they are. Carl Sagan famously said, "We are a way for the cosmos to know itself." And every time you learn something new about the universe, every time you look up at the stars with understanding rather than just wonder, you're fulfilling that role. You're part of the grand project of cosmic self-discovery. But let's come back down to Earth for a moment because there are practical reasons to study stars too. Understanding stellar physics helps us understand our own star, the Sun. And understanding the Sun helps us predict space weather, solar flares and coronal mass ejections that can interfere with satellites, power grids, and communication systems here on Earth. Studying massive stars helps us understand supernovae, which are crucial for understanding the chemical evolution of galaxies. Supernovae create and disperse heavy elements, enriching the interstellar medium and providing the raw materials for new stars and planets. Without supernovae, there would be no Earth, no oceans, no life. Understanding these explosions helps us understand our own existence. Moreover, supernovae are used as distance indicators in cosmology. A particular type called Type Ia supernovae have very consistent brightness, making them standard candles that astronomers use to measure distances to faraway galaxies. Observations of these supernovae in the 1990s led to the discovery that the universe's expansion is accelerating, driven by something we call dark energy. That discovery won the Nobel Prize in Physics in 2011. So, studying stars, even ones as exotic and distant as RSGC1 F01, has ramifications that extend far beyond just cataloging stellar sizes. It feeds into our broader understanding of the cosmos, from the smallest scales of nuclear physics to the largest scales of cosmic structure and evolution. And let's not forget inspiration. The images and discoveries from astronomy inspire people. They inspire artists, writers, filmmakers. They inspire young people to pursue careers in science. They remind all of us that we live in an astonishing universe full of beauty and mystery. In an age of cynicism and division, the cosmos offers something we can all share, a sense of wonder at the sheer scale and splendor of existence. When you see an image of the pillars of creation, or the swirling arms of a spiral galaxy, or an artist's rendering of a red supergiant like RSGC1 F01, you're reminded that reality is stranger and more magnificent than any fiction. We live in a universe where stars can grow large enough to swallow multiple planets, where galaxies collide and merge over billions of years, where black holes warp space and time itself. This isn't fantasy. This is the world we inhabit. And the best part? We're still in the early stages of understanding it all. The scientific revolution is only a few hundred years old. Telescopes have only existed for about 400 years. We've only been able to detect radio waves, X-rays, and other non-visible forms of light from space for less than a century. Space-based telescopes have only existed for a few decades. The Hubble Space Telescope launched in 1990. The James Webb Space Telescope launched in 2021. Each new technological advancement reveals things we never imagined. Hubble showed us galaxies in the distant universe, baby pictures of the cosmos when it was young. Webb is now peering even further back, looking at the very first galaxies that formed after the Big Bang. Future telescopes will see even more, pushing the boundaries of what's observable. And it's not just optical telescopes. We now have gravitational wave detectors like LIGO that can sense ripples in spacetime caused by colliding black holes and neutron stars. We have neutrino detectors buried deep underground that catch ghostly particles streaming from the sun and from supernova. We have radio telescope arrays spread across continents that work together to create virtual telescopes the size of Earth, allowing us to image things like the shadow of a black hole's event horizon. The Event Horizon Telescope collaboration did exactly that in 2019, producing the first image of a black hole's shadow in the center of the galaxy M87. That black hole, by the way, is another object of extreme scale, 6.5 billion times the mass of our Sun. If you think RSGC1 F01 is big, consider that this black hole's event horizon is about 19 billion kilometers across. You could fit multiple solar systems inside it. The universe specializes in extremes: the smallest, the largest, the hottest, the coldest, the densest, the emptiest. And somewhere in between all these extremes, there's a planet called Earth, orbiting an average star, home to billions of living creatures, including one species that has developed the ability to contemplate the cosmos that created it. That's remarkable. Against all odds, in a universe that's mostly empty space and radiation, on a small rocky planet in an unremarkable corner of an ordinary galaxy, matter has organized itself into patterns complex enough to think, to feel, to wonder. You are one of those patterns, and right now, that pattern is learning about stars 19,000 light-years away. Let me share something that always fills me with awe. The atoms in your left hand probably came from a different star than the atoms in your right hand. Think about that. The particles making up your body have individual histories stretching back billions of years. Some were forged in massive stars that exploded before our Sun even existed. Others might have been created in the Big Bang itself. The hydrogen in your body, for instance, is mostly primordial, dating back to the first few minutes of the universe's existence. These atoms have been on an incredible journey. They've been inside stars. They've drifted through interstellar space. They've been part of the gas cloud that collapsed to form our solar system. They've been incorporated into asteroids and comets. Some of them came to Earth during the planet's formation. Others arrived later, delivered by meteorites or comets. They've cycled through oceans and atmospheres, through countless organisms over millions and billions of years, and now, for this brief moment in cosmic history, they're part of you, arranged in the specific pattern that makes you you. Someday those atoms will be part of something else. The cycle continues. You're borrowing these particles from the universe for a little while, and then you'll return them. Nothing is truly created or destroyed. It just changes form. It just cycles through different patterns. Stars like RSGC1 F01 are part of that same cycle, just on a much grander scale. Right now, the star is fusing light elements into heavier ones, creating the building blocks of future planets and life forms. When it explodes, those elements will scatter across light years of space. Some will be incorporated into new stars. Some will become planets. And maybe, billions of years from now, some of those atoms will be part of a living creature on some distant world, looking up at their sky and wondering about the stars. It's a beautiful thought, isn't it? That the universe recycles itself, that everything is connected through this vast web of matter and energy cycling through different forms. Birth and death, creation and destruction. They're not opposites, but rather different phases of the same eternal process. Now, while we focused primarily on RSGC1 F01, I want to acknowledge that the quest to find the largest star is ongoing. Science doesn't stand still. New observations are being made constantly. New telescopes are being built. New techniques are being developed. It's entirely possible that by the time you're watching this, even newer data has emerged that shifts the rankings again. And that's okay. That's how science works. We make the best conclusions we can with the data available, knowing that future observations might change our understanding. The goal isn't to be right forever. The goal is to get progressively closer to the truth. There are other candidates for extremely large stars that I haven't mentioned yet. Stars like NML Cygni, another red supergiant in the constellation Cygnus, with estimates ranging from 1,650 to 2,770 solar radii, depending on which study you look at. Or KY Cygni, also in Cygnus, with estimates around 1,420 solar radii. Or AH Scorpii, a red supergiant variable star that pulsates, changing size over time. At its maximum size, it might reach 1,411 solar radii. The fact that it pulsates raises an interesting point. These giant stars aren't static. They breathe, in a sense, expanding and contracting over periods of months or years. So even asking, how big is this star? Becomes complicated, because the answer might change, depending on when you measure it. Then there are the uncertainties I mentioned earlier about measurement techniques. Different research teams using different methods sometimes arrive at different size estimates for the same star. This isn't because anyone is doing bad science. It's because the measurements are genuinely difficult, and different approaches have different systematic uncertainties. For example, one team might estimate size based on the star's luminosity and temperature using theoretical models of stellar atmospheres. Another team might use interferometry to directly measure the star's angular diameter in the sky, then combine that with distance measurements to get the physical size. A third team might use observations of the star's spectral lines, which can be affected by the star's size and the motions in its atmosphere. All three methods are valid, but they might give slightly different answers, and until we have even better data, maybe from next-generation telescopes, we have to accept that there's some uncertainty in the rankings. RSGC1 F01 is certainly among the largest stars known. Whether it's the absolute largest or whether that title belongs to another star might depend on exactly how you do the measurement and which uncertainties you consider most important. But you know what? That uncertainty doesn't diminish the wonder of it all. Whether the largest star is 1,500 solar radii or 2,000 solar radii, we're still talking about objects of almost incomprehensible size. We're still talking about stars so large that they challenge our ability to even visualize them properly. And that brings me to a question I often get. How can we even comprehend sizes this large? How do we wrap our brains around something 1,500 times bigger than our sun? The honest answer is that we can't. Not really. Our brains evolved to deal with objects at human scales. Trees, animals, rivers, mountains. These are sizes we can perceive directly and understand intuitively. Once you get much larger or much smaller than that, our intuition breaks down. We have to rely on analogies and mathematical comparisons, but even those fall short of giving us a true gut-level understanding. I can tell you that RSGC1 F01 could contain 6 billion suns, but what does that actually mean? Can you picture 6 billion of anything? I can tell you that light takes 7 hours to cross the star's diameter. But can you really grasp what that means in terms of size? These numbers are intellectually comprehensible, but not viscerally comprehensible. And that's okay. In fact, it's part of what makes astronomy so humbling and so exciting. We're dealing with scales that exceed human experience, that remind us how small we are in the grand scheme of things, but also how remarkable it is that we can measure and understand these objects at all. Think about the tools we've developed to extend our senses beyond their natural limits. Telescopes let us see farther than our eyes alone could ever manage. Spectrographs let us analyze light in ways that reveal the composition, temperature, velocity, and physical conditions of distant objects. Computers let us process and visualize data in forms our brains can work with. Mathematics gives us a language to describe things we can't directly experience. In a sense, science is humanity's way of overcoming our built-in limitations. We're not the fastest animals or the strongest or the most acute of sense. But we're tool makers. We're problem solvers. We can build instruments that extend our reach across the universe. We can develop theories that explain phenomena we'll never witness firsthand. We can collaborate across generations, building on the work of those who came before us. Every measurement of RSGC1 F01 size rests on centuries of accumulated knowledge. Newton's laws of motion and gravity, Einstein's theory of relativity, quantum mechanics and nuclear physics explaining how fusion works, the work of countless astronomers cataloging stars, measuring distances, developing spectroscopy, the engineers who designed and built telescopes, the programmers who wrote the software to analyze data, the educators who trained the scientists who made the discoveries. Science is a collective human endeavor. It's not about lone geniuses having sudden revelations, though those moments do happen. It's about communities of people working together, checking each other's work, building on each other's ideas, slowly and methodically expanding the boundaries of knowledge. And you're part of that community now, just by learning about these discoveries. You don't have to be a professional astronomer to appreciate what's been learned. You don't need a PhD to understand the basic principles. Science belongs to everyone who's curious, everyone who wants to know how things work, everyone who looks up at the night sky and asks questions. That's something I want to emphasize. Sometimes people feel intimidated by science, like it's only for experts with advanced degrees. But that's not true. The core of science, asking questions, looking for evidence, testing ideas, being willing to change your mind when the data demands it, these are things anyone can do. Professional scientists just happen to do it full-time with specialized training and equipment. But the sense of wonder, the curiosity, the desire to understand, that's universal. That's human. And that's what drives all scientific discovery, from the simplest observation to the most complex theoretical work. So when you learn that RSGC1 F01 is 1,500 times larger than the Sun, you're not just memorizing a fact, you're connecting with that deeper human impulse to explore and understand. You're participating in the grand project of figuring out what kind of universe we live in, and what a universe it is. A universe where stars can grow large enough to engulf planetary orbits, where galaxies containing billions of stars collide and merge, where space itself can bend and warp, where time flows at different rates, depending on how fast you're moving and how deep you are in a gravitational field, where quantum particles can be in multiple states simultaneously until observed, where the vast majority of the universe's content is dark matter and dark energy that we can't even directly detect. We live in a universe that's both stranger and more wonderful than our ancestors could have imagined. And we're still in the process of discovering just how strange and wonderful it really is. Let me tell you about some of the mysteries that remain, some of the questions we're still trying to answer about stars like RSGC1 F01. For instance, we don't fully understand the mechanisms that cause stars to shed mass as they approach the end of their lives. We know it happens. We can see the nebulae and shells of gas around these stars, but the detailed physics of how the mass is ejected, what triggers it, how much is lost, and at what rate, these are still areas of active research. We also don't completely understand the internal structure of these giants. Remember, the outer layers are incredibly diffuse, almost vacuum-like. But how does material circulate within the star? How do convection currents move energy and matter from the hot interior to the cool surface? What role do magnetic fields play? These questions are hard to answer because we can't see inside stars, and our computer simulations, while sophisticated, still make simplifying assumptions. Another mystery concerns the final fate of these stars. We know red supergiants like RSGC1 F01 will explode as supernovae, but predicting exactly when is impossible with current knowledge. Is it centuries from now? Millennia? Tomorrow? We simply don't know. The star could be stable for another 100,000 years, or it could have already exploded and the light just hasn't reached us yet. And after the supernova, what remains? Stars in the mass range of RSGC1 F01 probably leave behind neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons. But there's a threshold somewhere around 20 to 25 solar masses where the remnant becomes so massive that it collapses all the way to a black hole instead. Which fate awaits F01? We won't know until it happens. These unanswered questions aren't failures of science. They're opportunities. They're the frontiers where exciting research is happening right now. Graduate students are writing theses on stellar mass loss. Postdocs are running sophisticated simulations of supergiant interiors. Observing teams are using the latest instruments to study these stars in unprecedented detail. And every so often, someone makes a breakthrough. They notice something in the data that no one noticed before. They develop a new technique that improves measurements. They make a connection between seemingly unrelated phenomena that suddenly explains something that was mysterious. That's when science gets really exciting. When you realize you're seeing something no one has ever seen before, understanding something that was hidden until this moment. I sometimes wonder what it must have felt like to be the first person to realize that stars are actually suns like our own, just vastly more distant. That revelation came in the 1800s as astronomers began measuring stellar parallaxes and realized how far away stars really were. Suddenly, the cosmos expanded from a sphere of fixed stars just beyond the planets to an almost infinite expanse populated by countless suns. Or imagine being one of the astronomers in the 1920s, when Edwin Hubble proved that certain nebulae were actually entire galaxies beyond our own. Overnight, the universe grew by a factor of millions. What was once thought to be the entirety of creation, our Milky Way galaxy, became just one island universe among countless others. Or picture being on the teams that discovered the first exoplanets in the 1990s, proving that other stars have planets too, that our solar system isn't unique. That discovery opened up entirely new fields of research and sparked serious scientific inquiry into the possibility of life elsewhere in the universe. These paradigm shifts, these moments when our understanding fundamentally changes, are some of the most thrilling events in science. And they're still happening. The discovery of dark energy in 1998, the imaging of a black hole shadow in 2019, the detection of phosphine in Venus's atmosphere in 2020, which sparked debate about possible biosignatures. The incredible images from the James Webb Space Telescope showing galaxies as they appeared over 13 billion years ago. We're living in a golden age of astronomy and astrophysics. More telescopes, more data, more computational power, more international collaboration than ever before in history. Questions that were purely philosophical a century ago. How did the universe begin? Are there planets around other stars? What happens at the edge of a black hole? Are now subjects of observational science, and the study of giant stars like RSGC1 F01 fits into this broader picture. Understanding these objects helps us understand stellar evolution, nucleosynthesis, the chemical enrichment of galaxies, and ultimately the processes that made our own existence possible. You see, there's a direct line connecting RSGC1 F01 to you. Billions of years ago, stars similar to this one lived and died in the region of space that would eventually become our solar system. Those stars created heavy elements and scattered them into space when they exploded. That enriched material, mixed with gas and dust, eventually collapsed under gravity to form our Sun and the planets orbiting it. Earth incorporated those heavy elements, iron that formed the planet's core, silicon and oxygen that make up rocks, carbon, nitrogen, and all the other elements necessary for life. Without the death of earlier generations of massive stars, Earth would be nothing but hydrogen and helium. No solid surface, no oceans, no atmosphere capable of supporting life. So when you look at RSGC1 F01, you're not just looking at a distant astronomical object. You're looking at a star that's doing now what other stars did billions of years ago to make you possible. You're seeing your own deep cosmic history playing out in real time, just 19,000 light-years away. That's the power of astronomy. It connects us to the universe not just intellectually, but materially and historically. We are, quite literally, the universe looking at itself. We're patterns of matter organized in such a way that we can contemplate our own origins and our place in the cosmos. And what a privilege that is. Think about the odds. In a universe that's mostly empty space, where matter is the exception rather than the rule, we exist, on a planet with conditions stable enough for billions of years to allow life to evolve. As members of a species that developed consciousness, language, technology, and the ability to systematically investigate nature. At a point in history where we have the tools and knowledge to understand stars thousands of light-years away. The probability of all those factors coming together is astronomically small, yet here we are. And that makes this moment, this exact moment where you're learning about the largest stars in the universe, something special. You're living in a time when humanity has finally developed the capability to answer questions that our ancestors could only wonder about. Ancient peoples looked at the stars and created stories. The Greeks saw heroes and monsters in the constellations. The Chinese mapped the heavens and looked for omens. Indigenous cultures around the world incorporated celestial observations into their calendars, navigation, and mythology. These were sophisticated and meaningful ways of relating to the cosmos, but they were based on limited information and pre-scientific frameworks. Today, we have something different. We can measure the chemical composition of stars. We can trace their evolution from birth to death. We can place them in the context of galaxy formation and cosmic history. We understand the physics governing their behavior. We can make predictions that can be tested and verified. That doesn't make our ancestors' relationship with the stars any less valid or meaningful. It just means we've added layers of understanding that they couldn't access. And crucially, the scientific understanding doesn't diminish the wonder. If anything, it enhances it. Knowing that RSGC1 F01 is a nuclear furnace transforming light elements into heavy ones, that it's in the final stages of a life cycle that will culminate in a spectacular explosion, that its death will seed the galaxy with the materials for new worlds and possibly new life, all of this makes the star more amazing, not less. Science doesn't drain the magic from the universe. It reveals deeper magic that was hidden all along. The real story of stars, how they form, live, and die, how they create the elements that make up everything we know, is far more awe-inspiring than any mythology, precisely because it's true, and we're constantly learning more. One of the exciting frontiers in studying red supergiants involves trying to catch them in the act of exploding. For a long time, supernovae were discovered after the fact. We'd notice a new bright spot in a galaxy and realize a star had exploded. But with modern automated surveys that continuously monitor large portions of the sky, we're getting better at catching these events early, sometimes within hours of the explosion beginning. When we detect a supernova that quickly, we can immediately point other telescopes at it and watch how the explosion evolves. We can take spectra showing how the ejected material is moving and what elements it contains. We can look for neutrinos, ghostly particles that escape from the collapsing core and reach us before the light does. We can even try to identify what the star looked like before it exploded by examining archival images. This kind of time-domain astronomy, watching how things change over time, is revolutionizing our understanding of stellar death. Each supernova teaches us something new. Sometimes they behave as expected. Sometimes they surprise us with unexpected features that challenge our theoretical models. Both outcomes are valuable. And speaking of surprises, there's a category of stars even more extreme than red supergiants that I should mention, even though they may not exist anymore. These are called quasi-stars, and they're purely hypothetical objects that might have formed in the very early universe, within the first billion years after the Big Bang. A quasi-star would form if a black hole appeared at the center of a huge cloud of gas and began accreting material at a tremendous rate. The infalling gas would heat up and radiate enormous amounts of energy, inflating the surrounding envelope to truly staggering proportions. Theoretical models suggest quasi-stars could reach sizes of 10,000 solar radii, or even larger, 10,000 times the radius of our Sun. If such an object existed and you placed it where our Sun is, its surface would extend past the orbit of Saturn, past Uranus, maybe even past Neptune. But here's the thing: quasi-stars, if they existed at all, would have been incredibly unstable and short-lived. They would have consumed themselves in a few million years at most, and they could only form in the early universe, when conditions were very different from today. So, we'll never observe one directly. We can only speculate about them based on theoretical models and indirect evidence. Still, the fact that physics allows for the possibility of stars even larger than RSGC1 F01 is mind-boggling. The universe, it seems, has no shortage of extremes. Wherever we look, whatever we study, we find examples of nature pushing the boundaries of what's possible. And that's one of the beautiful things about physics. The same laws that govern a falling apple on Earth also govern the behavior of stars, galaxies, and the entire universe. Gravity works the same way everywhere. Nuclear fusion follows the same rules in our laboratory experiments as it does in stellar cores. Light propagates according to the same principles whether it's crossing your room or crossing the cosmos. This universality of physical law is what makes astronomy possible. We can study objects we'll never visit because we understand the fundamental rules they obey. We can decode the information carried by starlight because we know how atoms interact with radiation. We can model stellar interiors because we understand thermodynamics and nuclear physics. It's a testament to the power of scientific thinking that we can sit on Earth and figure out what's happening inside a star 19,000 light-years away. That's not magic, it's reason, mathematics, careful observation, and the accumulated knowledge of generations of scientists. But the result feels almost magical. Now, let's talk about what happens to a star like RSGC1 F01 in its final moments. We've mentioned supernova, but what does that actually mean? What happens during those last seconds of the star's life? Remember, the star has been fusing progressively heavier elements in its core: hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, neon to oxygen and silicon, and finally, silicon to iron. Each stage produces less energy and lasts for a shorter time. By the time the star has an iron core, it's living on borrowed time. Iron is unique among elements. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy. It's a dead end. The iron core can't support the star through fusion. For a while, electron degeneracy pressure, a quantum mechanical effect, holds the core up against gravity. But as more iron accumulates, the core grows more massive. Eventually, the core exceeds a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of the Sun. At that point, electron degeneracy pressure can no longer support the core. And what happens next is almost unimaginably violent. The core collapses. In less than a second, a sphere roughly the size of Earth compresses down to a sphere maybe 20 kilometers across. The density becomes so extreme that protons and electrons are squeezed together to form neutrons. What's left is a neutron star, effectively a giant atomic nucleus, with the mass of the Sun compressed into a sphere the size of a city. The collapse releases a staggering amount of gravitational potential energy, roughly 10 to the power of 46 joules. That's more energy than our Sun will radiate in its entire 10 billion-year lifetime, released in less than a second. Most of this energy escapes in the form of neutrinos, but even the tiny fraction that goes into the explosion is enough to tear the rest of the star apart. The outer layers, suddenly unsupported, fall inward toward the core. When they hit the rebounding shock wave from the core collapse, they're blasted outward at speeds of 10,000 to 30,000 kilometers per second, up to 10% of the speed of light. This ejected material, the star's entire envelope, including all those heavy elements created through years of fusion, expands into space as a supernova remnant. For a few weeks, the supernova outshines every other star in its galaxy combined. It's one of the brightest events in the universe. And then, over months and years, it fades, but the material it ejected continues expanding, slamming into surrounding gas and creating shock waves that compress the interstellar medium and trigger new star formation. The neutron star left behind is an object of extremes in its own right. A single sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. The surface gravity is billions of times stronger than Earth's. The magnetic field is trillions of times stronger than the strongest magnets we can create. Some neutron stars spin hundreds of times per second, beaming radiation into space like cosmic lighthouses. These are the pulsars we detect with radio telescopes. If RSGC1 F01's core is just a bit more massive than the Chandrasekhar limit, it might collapse all the way past the neutron star stage and form a black hole instead. In that case, no remnant remains except the black hole itself, a region of space where gravity is so strong that not even light can escape. Either way, neutron star or black hole, the death of RSGC1 F01 will be spectacular, and the enriched material it disperses will become part of the next generation of stars and planets. The cycle continues. This is the cosmic cycle of creation and destruction that has been ongoing for most of the universe's history. The first stars that formed after the Big Bang were made only of hydrogen and helium. Those were the only elements that existed. When those stars exploded, they created and dispersed heavier elements. The next generation of stars formed from material enriched by that first generation. They in turn created more heavy elements and exploded. With each successive generation, the universe's complement of heavy elements increases. Astronomers call this metallicity, the abundance of elements heavier than hydrogen and helium. Our Sun is a relatively high metallicity star, meaning it formed from material that had already been processed through multiple generations of earlier stars. Earth and everything on it exists because of this multi-generational enrichment. The iron in your blood passed through at least one supernova, possibly several. The calcium in your bones, the oxygen you breathe, the carbon in every organic molecule in your body, all of it came from stars that lived and died before our solar system even existed. You are, quite literally, the product of stellar alchemy stretching back billions of years. You're made of atoms that have been on an incredible journey through the cosmos, cycling through different stars, drifting through interstellar space, eventually coming together in the specific arrangement that makes you possible. And RSGC1 F01 is continuing that process right now. In its core, at this very moment, nuclear reactions are creating elements that don't exist naturally on Earth. When it explodes, those elements will be scattered across dozens or hundreds of light years. Some of that material will eventually be incorporated into new stars and planets. And maybe, billions of years from now, some of those atoms will be part of a living creature. And that creature will be contemplating the stars just as you are right now. It's a beautiful thought. We're all connected through this vast network of stellar birth, death, and rebirth. Every atom in your body is a temporary arrangement, borrowed from the universe for a brief time, soon to be returned and recycled into something new. Nothing is permanent. Everything flows. The universe is a constant process of transformation. The ancient Greek philosopher Heraclitus said, "You cannot step into the same river twice." He was talking about change and impermanence, about how everything is always in flux. And he was right. The atoms in your body are being replaced constantly. The cells in your body die and are regenerated. You're not the same physical person you were 7 years ago. almost every atom has been replaced. The same is true on cosmic scales. Stars are born, live and die. Galaxies collide and merge. Even the universe itself is evolving, expanding, cooling, changing its structure over time. Nothing is static. Everything is a process. And understanding this, really grasping the dynamic, evolving nature of reality, can change how you see everything. You're not a fixed thing, but a pattern, a process, a temporary arrangement of matter and energy that is conscious and aware. You're a wave in the ocean, distinct for a moment, but ultimately part of the larger whole. This might sound philosophical, and it is, but it's grounded in hard science. Physics tells us that matter and energy are conserved, that they transform, but don't disappear. Biology tells us that we're part of a continuous chain of life stretching back billions of years. Astronomy tells us that we're made of material created in stars and recycled through the cosmos. All of these insights from different scientific disciplines point to the same profound truth. We're part of something much larger than ourselves. We're participants in the grand cosmic drama that's been unfolding for nearly 14 billion years, and that's both humbling and empowering. Humbling because it reminds us how small we are in space and time. Empowering because it shows us that we're connected to everything, that we're made of the same stuff as stars and planets, that we're the universe's way of knowing itself. So when you look up at the night sky and think about stars like RSGC1 F01, remember that you're not just looking at distant objects, you're looking at your cosmic relatives, you're looking at the processes that created you, you're looking at your past, and in a sense at your future as well. The atoms in your body will outlast you. Long after you're gone, they'll be part of other things. Maybe a tree, maybe the ocean, maybe the air someone else breathes. Eventually, billions of years from now, they might be incorporated into a new star, fusing into heavier elements, experiencing the same nuclear alchemy that created them in the first place. Nothing is lost. Everything is transformed. That's the law of conservation of mass energy, but it's also a profound statement about the nature of existence. Now, as we near the end of our journey through the story of the largest stars, I want to circle back to where we began, with the question of which star is truly the biggest. And I want to emphasize again that the answer isn't as straightforward as it might seem. RSGC1 F01 is currently one of the best candidates, with relatively reliable measurements suggesting a radius around 1,500 solar radii. But as we've discussed, other stars like UY Scuti, Stephenson 218, VY Canis Majoris, and others are also in the running, depending on which measurements you trust and how you handle the uncertainties. The title of largest known star might shift as new data comes in. That's not a bug in the scientific process. It's a feature. Science isn't about having all the answers immediately and permanently. It's about progressively refining our understanding as we gather more and better information. In a few years, we might have new measurements from next-generation telescopes that clarify the sizes of these stellar giants with greater precision. Or we might discover an even larger star that we haven't detected yet. The universe is vast, and we've surveyed only a tiny fraction of it in detail. What won't change is the fundamental fact that these objects exist, stars hundreds or thousands of times larger than our Sun, nearing the end of their lives, destined to explode and enrich the galaxy with heavy elements. That's not a detail that will be revised away. The specifics might change, but the big picture is solid. And really, the specific ranking matters less than the broader understanding. Whether the largest star is 1,500 or 2,000 solar radii doesn't change the essential story. That stars can grow to almost unimaginable sizes, that they represent an extreme of what's possible in stellar evolution, that they're part of the cycle that creates and distributes the building blocks of planets and life. The quest to identify the largest star is valuable because it pushes us to develop better observational techniques, to refine our theoretical models, to understand the limits of stellar physics. But the real treasure isn't the final answer. It's everything we learn along the way, every measurement we make, every observation we analyze, Every model we build adds to our collective understanding of how the universe works. And that understanding has value beyond just satisfying curiosity, though satisfying curiosity is valuable in itself. Understanding stars helps us understand our Sun and how it affects Earth. It informs our search for habitable planets around other stars. It helps us interpret the light from distant galaxies and understand cosmic history. It connects to fundamental physics, chemistry, and even biology. Knowledge in one area illuminates other areas. Science is an interconnected web of understanding, and every new thread we add strengthens the whole. So whether RSGC1 F01 holds the record for largest star, or whether that honor belongs to another stellar giant, the important thing is that we're asking the question, making the measurements, and deepening our understanding of these incredible objects. And you, by learning about this, are participating in that process. You're not a passive observer. You're an active participant in humanity's grand project of understanding the cosmos. Every time someone learns something new about the universe, the collective human knowledge increases. Every time someone shares that knowledge with others, the benefit multiplies. That's what education is really about, not just transferring facts from one person to another, but expanding the circle of understanding, bringing more people into the conversation, ensuring that the knowledge we've worked so hard to acquire doesn't stay locked away in academic journals, but becomes part of our shared human heritage. The story of RSGC1 F01 and the quest to find the largest star is part of a much larger story, the story of humanity's relationship with the cosmos. For most of our existence as a species, the sky was a mystery. The stars were lights of unknown nature. The planets were wandering points of light. The Milky Way was a band of diffuse glow across the heavens. Our ancestors didn't know what any of it was, but they looked up anyway. They wondered. They asked questions. They created stories to explain what they saw, and eventually some of them started observing systematically, keeping records, noticing patterns. That was the beginning of astronomy. Over thousands of years, through countless observations and insights, through the work of people across many cultures and continents, we've transformed our understanding from mythology to science. We've gone from thinking the stars were tiny lights on a celestial sphere to knowing they're distant suns, many of them far larger and more luminous than our own. We've gone from Earth-centered cosmology to understanding our place as one planet among billions in a galaxy that's one among trillions. And we're still in the middle of that journey. We haven't answered all the questions. We probably never will. Every answer seems to generate new questions. But that's what makes it exciting. There's always more to discover, always another mystery to investigate, always a deeper level of understanding to reach for. RSGC1 F01 represents one small piece of this vast puzzle. It's a single star in a single cluster in a single arm of a single galaxy. But by studying it, we learn principles that apply to stars throughout the universe. We learn about stellar evolution, nuclear physics, the creation of elements, the life cycle of matter. We learn about our own origins and our connection to the cosmos. And perhaps most importantly, we're reminded of something that's easy to forget in our day-to-day lives, that we live in an astonishing universe. A universe where matter can organize itself into structures as simple as hydrogen atoms and as complex as human brains. A universe where physical laws operate with mathematical precision across billions of light years and billions of years of time. A universe that, as far as we can tell, is comprehensible, that follows rules we can discover and understand. That comprehensibility isn't something we should take for granted. The universe didn't have to be understandable. It could have been chaotic and random, governed by no consistent laws. But it's not. It operates according to principles that we can discover through observation and reason. That's remarkable. And the fact that we, a species that evolved on one small planet, have the cognitive capacity to understand these principles is equally remarkable. We can do mathematics that describes the curvature of spacetime. We can build instruments that detect light from the edge of the observable universe. We can create models that accurately predict stellar evolution over billions of years. Our brains, which evolved to help our ancestors find food and avoid predators, can also comprehend quantum mechanics and general relativity. That's not something to gloss over. The fact that the universe is comprehensible and that we have the ability to comprehend it is one of the deepest mysteries and greatest gifts of existence. So when you think about RSGC1 F01, think about more than just its size. Think about what it represents. Think about the chain of discovery that led us to find it, measure it, understand it. Think about the journey that stars' atoms have been on and will continue on after the star explodes. Think about your own connection to that cosmic process. You're made of stardust. That's not a poetic metaphor, it's literal truth. The atoms in your body were forged in stars that lived and died before our sun existed. You're a way for the universe to know itself. You're a pattern of matter that has become conscious and aware, capable of contemplating the very cosmos that created you. And in this moment, you're using that consciousness to learn about one of the largest stars known to exist. You're reaching across 19,000 light-years of space and almost 20,000 years of time to understand an object you'll never visit, never touch, never see with your naked eye. But through science, through reason, through the accumulated knowledge of our species, you can know it. You can understand it. You can appreciate it. That's the power of human curiosity and intelligence. That's what makes us special. Not that we're separate from nature, but that we're the part of nature that can understand itself. As we close this exploration, I want to leave you with a challenge and an invitation. The challenge is this: the next time you look up at the night sky, really think about what you're seeing. Those aren't just pretty lights. Each one is a sun, possibly with planets, possibly with life. Some are larger than our sun, some smaller, some are younger, some older, some are in the prime of their lives, others are dying. And beyond what you can see with your eyes, there are billions more. Galaxies beyond counting, stars beyond number, worlds we can barely imagine. All of it governed by the same physical laws, all of it part of the same cosmic story that includes you. The invitation is to stay curious, keep asking questions, keep learning. Science isn't just for scientists, it's for everyone who wonders how things work, who wants to understand the world and the universe we're part of. There are incredible resources available now: books, videos, podcasts, websites, even free online courses from major universities. The knowledge is there for anyone who wants it. And when you learn something new about the universe, share it. Tell your friends, your family, your children. Post about it. Discuss it. Keep the conversation going. Knowledge grows when it's shared, and wonder multiplies when it's experienced together. The story of RSGC1 F01 is still being written. More observations will be made. More data will be analyzed. Our understanding will deepen. And perhaps someday, maybe in our lifetime, maybe not, we'll witness the spectacular finale when this stellar giant explodes and seeds the galaxy with the heavy elements it spent millions of years creating. When that happens, when the light from that supernova finally reaches Earth after its 19,500-year journey, there will be a new bright star in the sky, visible even in daylight for weeks or months. Ancient astronomers would have interpreted it as an omen. We'll understand it as the death of a star, the culmination of nuclear processes that began millions of years ago, the dispersal of material that will eventually become part of new stars and planets, and perhaps new life. And we'll watch it with our telescopes and our detectors, gathering data, analyzing spectra, measuring light curves, learning everything we can from this cosmic event. We'll see theory confirmed or challenged. We'll witness one of the universe's most powerful phenomena up close. Well, as close as 19,000 light-years allows. It will be a reminder that the universe is dynamic, evolving, constantly changing. Nothing lasts forever. Stars are born, live and die. Galaxies form and merge and evolve. Even the universe itself had a beginning and will have some kind of ending, whether that's heat death or a big crunch or something else we haven't predicted. But in this moment, right now, we're here. Conscious, aware, capable of understanding our place in the cosmos. We're made of atoms forged in ancient stars, arranged in patterns that can think and feel and wonder. We're the universe experiencing itself, studying itself, marveling at its own complexity and beauty. RSGC1 F01, 1,500 times the radius of our Sun, containing the mass of dozens of suns, shining with the light of hundreds of thousands of suns, sits in a dusty cluster 19,500 light-years away, nearing the end of its life. It's one star, among hundreds of billions in our galaxy, in a universe containing trillions of galaxies. But it's also a teacher. It teaches us about physics and chemistry, about birth and death, about connection and cycles. It reminds us where we came from and connects us to the grand cosmic story that's been unfolding for nearly 14 billion years. And that's why we study the stars. Not just to measure and catalog them, but to understand ourselves through them. We're all made of star stuff, all part of the same cosmic family, all participants in the same vast unfolding story. So the next time someone asks you, "What's the largest star?" you can tell them about RSGC1 F01. But more importantly, you can tell them what it means, what it teaches us about the universe and our place in it. You can share the wonder of knowing that such objects exist, that we can measure and understand them despite the vast distances separating us. And maybe, in sharing that knowledge, you'll inspire someone else to look up, to wonder, to ask questions, to learn. That's how human knowledge grows, not just through professional scientists making discoveries, but through all of us sharing what we learn, passing on the sense of wonder, keeping curiosity alive from one generation to the next. Thank you for joining me on this journey through the cosmos to explore one of its largest inhabitants. Keep looking up, keep wondering, keep learning. The universe is vast and ancient and strange and beautiful, and it's yours to explore, at least in mind and imagination. The stars are waiting, and they have so much more to teach us. Have you ever wondered why we haven't come back to the moon yet? The video on the screen reveals the forgotten challenges, engineering hurdles, lost knowledge, and political realities that make returning to the moon much harder in the 21st century.